Good afternoon, or good morning as the case may be, and welcome to this webinar, Know the Unknown, using sensor fusion to identify toxic chemicals. This event, brought to you by ISHN Magazine, is sponsored by Ray Systems. I'm your moderator today, Dave Johnson, editor of ISHN Magazine, and I thank you for joining us. Our presenter today is Michael Weinstein. Michael is currently the Global Product Marketing Manager for handheld monitors and wireless infrastructure at Ray Systems. He joined Ray Systems in 2010 and manages several key product lines, including the 3000 series photoionization detectors, PIDs, for volatile organic compounds, such as the UltraRay 3000 PID with benzene specification, which is industry's premier tool for monitoring contamination from and worker exposure to benzene. Michael holds a Master's of Business Administration degree from the University of California at Berkeley. Now, before we begin Michael's presentation, I want to provide you with a few housekeeping items. At the bottom of your screen, you'll see a taskbar. Each icon on the taskbar is assigned to a particular element of today's webinar. If you are unsure about what an icon does, hover over the icon with your mouse and a box will pop up that tells you the function. A copy of Michael's presentation is located in the handouts icon. Today's presentation may be eligible for 1 hour of American Board of Industrial Hygiene certification maintenance credit. See the ABIH website for certification maintenance credit criteria. To receive the credit or certificate of completion, please take the quiz located in the handouts icon. Please take our survey following the webinar by clicking on the survey icon in the taskbar. Below the presenter's photo, there is a blank questions box that will allow you to type a question in the box and then hit the submit button to send it to us. Later in today's program, Michael will address as many questions as time permits. Now, today's event is being recorded and archived on www.ishn.com. All registered participants will receive an email within 1 or 2 business days that has a link to view a recording of this event. And now, I'm excited to turn it over to today's presenter, Michael Weinstein.
Thank you, Dave. Good afternoon, everyone. We appreciate you taking the time to join today's webinar. Today we're going to talk about how you can combine various sensor technologies, something we refer to as sensor fusion, to add value to identifying and quantifying toxic and combustible chemicals. Specifically, we're going to look at existing portable gas detection technologies and review their pluses and minuses. We're going to look at their limitations and see how using sensor fusions can help us overcome these limitations. We're going to look at specific examples where sensor fusion could provide better results than using individual gas detection technologies in isolation. We're hoping that we will be able to share some ideas with you today about how to combine different sensing technologies so that you can have an easier time solving the following problems, which are pretty common among a very wide range of our customers, and I'm sure a lot of you will find these issues, these topics relevant to your daily routines and daily jobs. So specifically, first thing we're going to look at is how you can use multiple different sensing technologies to identify and measure an unknown chemical, something we call speciation. We're going to look at industrial applications and emergency response situations. Now we're going to look at how multiple different technologies can be used to measure a particular chemical across a broad range of applications. And that, a broad range of concentrations, of gas concentrations for that specific chemical, starting from toxicity levels to monitor worker exposure to leak detection and larger spills where a broader population can be involved and a potential explosion hazard can be a possibility. Now we're going to look at how sensor fusion can help you confirm the reading obtained by a particular sensing technology with another technology, which is independent, which uses a different detection principle. And we'll see how it all can be achieved in a cost-effective and easy-to-use fashion. So this slide provides a quick overview of select portable detection technologies. And I'd like to make a disclaimer here that it is not our goal to really provide a comprehensive survey of all the portable detection technologies available to you. These are just some of the technologies that we want to look at here. And we're going to look at the pluses and minuses and look at some potential limitations of these technologies if they were to be used in isolation. So for example, if you look at the badges, right, that people would wear and then send them in at the end of the day to the lab for analysis, right? These badges are highly selective, right? They actually tell you which gas a person was exposed to. They're fairly broad in range, but the limitation of this technology is that the results are available post factum and lab analysis is expensive. If you look at the analytical equipment that is also available in a portable format or somewhat portable formats such as gas chromatographs and different spectrometry and spectroscopy equipment. These tools are selective and they're broad in range, but they're very costly. The gas chromatographs provide a snapshot-only measurement versus a continuous measurement. They're fairly bulky compared to portable gas detection instruments that we're used to. They usually provide no real-time alarms, even though they do provide an alarm when you do the analysis, but it's not a real-time alarm. And a very important consideration here is that these technologies are really, they really require special training. Now, electrochemical sensors are very, very broadly used across different industries for gas detection and personal protection. Such sensors are usually selective in nature. They have limited range. They usually don't go into high, very, very high ranges. There is a limited selection of such sensors available, even though it's getting wider and wider. But there are substances like benzene, for example, for which there is no electrochemical sensor available. Now, electrochemical sensors are also prone to cross-sensitivities, meaning that gases other than the target gas for a particular electrochemical sensor can cause the sensor to produce a reading. Or, even worse, cross-sensitive gases to which the sensor is negatively cross-sensitive can actually cause the sensor to underreport the readings for the target gas, which is a big safety concern. Electrochemical sensors can also be affected by temperature and humidity. Now, if you look at the catalytic combustible sensors, or something that we refer to as LEL sensors, lower explosive limit sensors, are not selective as a broadband sensors, and they usually measure within 0 to 100% of lower explosive limit range. So they stay within the LEL range. These sensors are susceptible to poisons and contaminants, meaning that some substances, like sulfur compounds, for example, and silicones, can actually negatively affect the sensor and prevent the sensor from working properly. and some heavier hydrocarbons, larger hydrocarbon molecules have a hard time actually getting through the flame arrestor of such a combustible catalytic sensor, and these sensors cannot detect them all that well. Photoionization detectors are another example of a broadband sensor that does not provide a selective measurement of a gas. Rather than saying, this is what I see, they say, I see something. But they can see a very wide range of different compounds. In terms of the measurement range, they're fairly broad. Photoionization detectors can go from parts per billion up to about 15,000 parts per million. But there are some compounds that are not ionizable, and therefore a photoionization detector cannot see such compounds like hydrogen, for example, methane. Now, flame ionization detectors are also a broadband tool. They're not selective to a particular compound. They would rather say that, there is something in the air. They're broad in range, but they require a hydrogen cylinder to operate because the flame that's used to ionize the chemical is basically a hydrogen flame. They're bulkier than PIDs, for example, and they're costly. Infrared, non-dispersive infrared sensors used in portable equipment, they are limited in terms of the range of compounds that they can detect, mostly used for hydrocarbons and carbon dioxide. They're fairly broad in range as well. Metal oxide semiconductor sensors are non-selective. They're broadband as well. This is one of the older sensing technologies. Still used fairly widely in the industry. Have their limitations in the sense that they're not as linear, not as accurate, and cannot really detect at parts per billion levels, such as a more sensitive photoionization detector would. These sensors are also affected by temperature, humidity, and poisons. Colorimetric tubes, one of the basic workhorse type of gas detection tools that have been used in the industry for a very long time. They are selective in terms of they're able to measure a concentration of a particular compound. And they are fairly broad in range. They would not normally cover a very high concentration in the range of high percent volume. They also provide a snapshot-only measurement. They cannot monitor a compound over time. It's like a photo versus a video. They're less accurate. They're more subjective when their readings are being interpreted. They're also slow to respond. So that's a quick survey of the sensing technologies that we're going to be looking at in this presentation. As I said, all of these technologies have their place in the industry. They do a very good job for the applications for which they are designed. Right? The reason why I'm using the term limitation here, or disadvantage, or challenge, is really not to diminish their significance, their importance, or their effectiveness in what they do, but to show that when they're used in isolation, we may not be able to achieve the results we want compared to combining them. Right? We can add value by combining these technologies. And sensor fusion does exactly that, right? Sensor fusion can be implemented in several ways. Like, for example, you can use several different sensors that can complement each other, right, for the objectives that we're going to look at in a second. In one multi-sensor, multi-gas instrument, like we refer to them. So, for example, you can have a photoionization detector and an electrochemical sensor, let's say for ammonia, for example. And then you have two independent, different detection technologies that you can use in one multi-gas instrument for ammonia. Now, for Another option is to look at different instruments or different types of instruments for the purpose of doing the sensor fusion, right? And aggregating data from such different distinct instruments to get the benefits of sensor fusion. We're going to look at both options here in the forthcoming slides. So conceptually, what is our approach that we would like to discuss here for sensor fusion from a high level standpoint here, right? And maybe these are going to be some ideas that you will find useful for your applications, for your day-to-day jobs. So when we're looking at identifying an unknown compound, what we're talking about here, when we say use sensor fusion to identify an unknown compound, we're thinking that it would be beneficial to use a broadband detection tool to identify that there is a chemical present in the atmosphere, right? And in many cases, you would actually know what spectrum of chemicals would be present at your facility, for example, or at an accident site. Now, you can use a broadband detection tool to determine that something is there in a certain concentration, and then you can use a speciation tool or a tool that is capable to detect a chemical in a specific fashion. Not just say that, there is something in the atmosphere, but a tool that can tell exactly what's in the atmosphere. So, for example, if you have a spill or a release at your facility, and you suspect that it could be, methylene chloride, for example, or benzene, you can use a PID or a photoionization detector to make sure that there is something, or to find the source of a leak, for example. And then you can use a specific tool, such a benzene tube, to actually determine how much of a particular chemical is present in that release, right? From the cost-effectiveness standpoint, for example, we know that analytical equipment is fairly costly. So if you look at a combination of a photoionization detector and a colorimetric tube, right, in many cases, their combination can approximate the selectivity and the performance of a gas chromatograph without the cost, right? So one of the goals of our today's webinar is really to come up with sensor fusion solutions and approaches that are cost-effective and easy to use, right? That was our goal from the start. So this is our potential suggestion, one option you can use to identify an unknown chemical using sensor fusion. Now, the second need, or the second issue that we're trying to help you address with this webinar is to be able to measure a chemical throughout its concentration range. In many cases, the same chemical can be both toxic and combustible in nature. So at a lower concentration, it can be toxic. At a higher concentration, it can be flammable, right? So in many cases, it is important for you to be able to measure that chemical at different concentrations. So when we're talking combustible gases, combustible hydrocarbons, what you could do, you could use a multi-gas instrument that has both an infrared combustible sensor and an LEL, or catalytic combustible sensor. This way you can measure a chemical within the LEL range. That is basically when you're going to make a stop work decision, usually at 10% LEL. If a chemical is present at that concentration, then you want to stop work. If you need to go higher towards the percent volume range, you can use an infrared or a thermal conductivity sensor. Going back to toxicity, what you can do is you can use an electrochemical sensor or tubes to do specific measurements of a chemical at its lower concentrations. And if you go into the higher concentrations, you can use a broadband tool that is capable of providing an accurate measurement at higher concentrations. So in many cases, you can use a PID or an FID for a very accurate measurement at, in a broadband fashion at both toxic concentrations and higher concentrations that include the flammability range and beyond, right? If you want to go into percent volume for combustible chemicals, like for example we're talking about it, you should use an infrared or thermal conductivity sensor to go into the percent volume range. And this is more relevant to applications such as pipeline maintenance and pipeline repairs, where there is a requirement to for purging, and then there is a need to observe the concentration of a combustible gas go from higher 90% to basically close to zero. So you can use different sensing technologies to measure a chemical throughout its range of concentrations. Now, the third objective that we ventured to offer you some solutions for is using multiple sensors that deploy unrelated technologies to measure the same chemical to cross-validate each other. And why is it relevant? Imagine a situation where you have an electrochemical sensor. We talked about cross-sensitivity as being one of the important limitations of the electrochemical sensing technology. And if you have an electrochemical sensor that you're using in an environment where potentially there could be a cross-interfering gas present. So in that scenario, you want to make sure that the readings you get on the electrochemical sensor are not affected by the cross-interfering gas. So what you would do, you would use another technology to validate that. So let's say if you look at chlorine, for example, right? Then your electrochemical sensor for chlorine is going to be negatively cross-sensitive to hydrogen sulfide. We have a case study on that we're going to cover later. So as a result, what you want to do is, in case you were doing confined space entry where both chlorine and hydrogen sulfide can be present, you want to use the electrochemical sensor and validate it with tubes, for example. Right? For ammonia, you can use an electrochemical sensor for ammonia and a photoionization detector to cross-verify. So if you're getting a reading for ammonia on the electrochemical sensor and a similar reading on the PID, then you may be almost positive that that is the actual concentration of ammonia in the atmosphere. Another option to cross-validate is to using, for example, for jet fuels. That's a good example where a compound is both toxic and combustible. So at the combustible levels, you can use an LEL sensor as well as a PID sensor. You can use the PID to validate the LEL sensor, especially in situations where you're measuring heavier hydrocarbons, like some of the jet fuels that have a hard time being recognized and measured by the LEL sensor. So when in doubt, use a PID with the LEL sensor for jet fuels. Now for hydrogen, that one can be detected both by an LEL sensor and a specific electrochemical sensor that's available for hydrogen at lower concentrations. So that's another option to actually measure hydrogen at throughout the concentration range, and in some cases cross-validate the readings obtained by one technology with another non-related technology. Now I'd like to go over some case studies, some specific examples of how sensor fusion can be used to really address the three big needs that we are covering throughout this presentation. So the first one was to identify and measure an unknown chemical. And the specific example I want to use here is how to identify and measure benzene, especially in situations where benzene can be present as part of a mix of many volatile organic compounds that are present at a refinery, for example. So before we go into the actual detection technique using sensor fusion, let's take a quick look at what benzene is. I know I've seen that we have some of our good customers attending the webinar, and a lot of them are very intimately familiar with benzene detection. But really quickly, for those of you who are not, who don't deal with benzene on a regular basis and may only be exposed to it on in an accidental, sporadic fashion. What is benzene? So benzene is really a major, very important industrial chemical. It is a precursor to a lot of different products that range from plastics, to pesticides, to pharmaceuticals. It is a very important chemical, but it's also a very, very toxic chemical. Benzene is naturally present in crude oil. So it is basically exposure to benzene can occur at a drilling rig, for example, right? Not only at a plant that actually produces benzene or processes benzene. Benzene is also a component of gasoline. And benzene, thanks to benzene, they're no longer using lead in gasoline. And here is just a brief example of the industries that are intimately involved with either production, use, or transportation of benzene. So these are the usual suspects. Oil and gas, chemical, and petrochemical industries are probably the biggest range of industries involved with benzene. Chemical manufacturing, very, very large there. Others you can see here. Storage facilities and transportation services, of course, handle benzene on a regular basis. Now, benzene is a liquid. In color, it ranges from basically transparent, colorless to light yellow. It has a very pleasant, sweet odor. So pleasant that back in the day, benzene was used as an aftershave lotion. It was, of course, until before its really high toxicity and carcinogenity was discovered. So now it's no longer used as an aftershave lotion. It was also used as a means to decaffeinate coffee. Now, benzene is not only toxic, extremely toxic to be exact, it's also highly flammable. So at 1.2% volume, it reaches its lower explosive limit. Okay? So the stop work limit for benzene is 1200 ppm, 10% LEL. Now, benzene is more toxic than most volatile organic compounds present at a refinery, and there are a lot of those. Okay? So the permissible exposure limit, according to OSHA, is 1 ppm. But the recommended exposure limit, according to NIOSH, is 0.1 ppm. So where our customers really focus on is the 0.5 ppm range for industrial hygiene purposes, most of our customers. And the concentration that's immediately dangerous to life and health is 500 ppm. So it is really, really toxic. So now imagine a situation if there is a major release of VOCs at a facility, or there is an overflow of a transport carrying benzene. And these are the potential problems that can occur in such circumstances. So first of all, you can get your workers an excessive exposure to benzene. And that is not good because benzene is a known carcinogen. It was scientifically and statistically linked to leukemia and other types of cancer, reproductive harm. So exposure to benzene is really something that industrial hygienists pay a very, very close attention to. So excessive worker exposure is a problem. And then flammability. We saw that benzene is highly flammable. So you would potentially have to tackle these two issues. So operationally, what would you need to do in terms of detection and measurement objectives? You will need to identify whether benzene is present in a release. And if yes, you need to know how much benzene specifically your workers got exposed to, right? And you need to be able to monitor for benzene across its concentration range for toxicity and flammability. Of course, these are some of the goals. You'll have other issues to deal with in terms of the cleanup and potential evacuation decisions, depending upon the concentration and the scope of an accident. But we're just covering the detection part here. So what are your options in terms of using portable equipment? So if you look at the individual sensing technologies that we briefly reviewed earlier, right? You can use a PID, a photoionization detector, or a flame ionization detector. to really cover the toxicity to flammability range, right? So a PID would go out to 15,000 ppm, and we saw that the lower explosive limit for benzene was 12,000. So a PID can detect benzene at concentrations from the parts per billion range out to its lower explosive limit. Same for an FID, a flame ionization detector. So these tools can be used fairly well for benzene across its concentration range, right? And in some cases, really, our customers are creative and resourceful enough to actually just limit, in many cases, the arsenal of portable detection tools to just a PID to make decisions on the benzene concentrations. For example, if you know that you have a release at a particular unit and you have a mix of volatile organic compounds, such as gasoline, for example, right, which is a mix of different chemicals, right? And you know, for example, that the gasoline that you produce contains a certain percentage of benzene. So when you use a photoionization detector, you can get a total VOC concentration present in the air, and then you can calculate which percentage normally benzene constitutes out of the mix that's being released, and you can make decisions on the actual concentration, on the actual maximum concentration of benzene that can be present in the atmosphere, right? But it's still not a specific way of detecting benzene, right? But let me continue with the individual sensing technologies. So flammability for benzene can be measured by a catalytic bead LEL sensor, a very, very widely used sensor, but you are actually stuck within the percent LEL range there. You cannot use that sensor to measure for toxicity. You can also use colorimetric tubes for benzene to measure within the toxicity range separately, right? There are also other technologies that and other tools that are available to measure benzene. Like, for example, we have our own Ultrarate 3000 photoionization detector-based tool that has a filter that filters out all other VOCs but benzene. So the reading that you get on your photoionization detector is actually a benzene-specific reading because other chemicals are being filtered out, right? The Ultrarate 3000 also offers you an opportunity to get a calculated STEL, short-term exposure limit for industrial hygiene purposes, to benzene. You can also monitor at a very, very granular level, down to 50 parts per billion, in 50 parts per billion increments. So, but what we're looking at is less specific tools, less technical tools. Ease of use is something that is of importance for our discussion here. So you can use sensor fusion to use basically basic tools and detect benzene throughout its concentrations range and in a specific fashion. So you can use a regular photoionization detector. We recommend that you use a 9.8 electron volt lamp because this way you can weed out other chemicals that can be present at a refinery, for example. One of them would be ethylene, right? And this way your PID becomes kind of more specific by reducing the number of possible chemicals that it sees, that it includes in the reading that it produces. Once you've taken a measurement with a PID, which is a broadband tool, you can actually use a colorimetric tube for benzene to determine a particular concentration of benzene, right? So the sensor fusion suggestion in this scenario is combining a broadband detection tool, such as a PID, with a specific tool, such as colorimetric tubes, for a cost-effective, easy-to-use way of measuring and detecting benzene. As a friendly reminder, there is not an electrochemical sensor for benzene, so that is not an option. So in summary, if you have a pure benzene release for some reason, if the concentration exceeds 1.5 parts per million, which is the olfactory threshold, the odor threshold, you should be able to smell it. So this would give you one clue. And then you can use a broadband detection tool to determine that something is present at a toxic level or at a combustible level. And you can use tubes to detect and determine that what part of the reading, of the total VOC reading that you get on your PID is accounted for by benzene. So that was the example of how you can use sensor fusion to speciate benzene. And now we have a polling question. Dave, back to you.
Yeah, this is Dave Johnson, your moderator again. And Michael has worked several polling questions into the presentation, as you'll see as Mike goes along. First question is pretty basic. Was the above information that Michael presented useful to you? Yes or no? And as you'll be able to see in the bar chart in the second half of the slide, Michael seems to be doing a pretty good job of relaying useful information to the audience. He's getting a 95% plus affirmative on the information being useful. Certainly the first 20 or so slides that Michael put together was chock full of very detailed information, very useful comparisons on the different tools that are available, and I think he did a quite good job of presenting an objective overview of the tools that are available to you. And it seems as though there's about 100 people in our virtual hall today, virtual forum, listening to Michael, and 95% are saying yes, this information that Michael's putting out there is indeed useful. With that, as you can see, 95%, very good. We do have a, going through the audience and who is attending, and as Michael mentioned, some are customers certainly of Ray Systems. The topic of this webinar is pretty technical, and you need a certain amount of sophistication, I believe, to be able to really absorb this information. And I think it says something about the quality of the audience that this presentation has attracted, that we're getting such a high positive percentage, 95%. Back to you, Michael.
Thanks, Dave. Thanks to our viewers for taking the poll question. Hopefully, the remaining material will be perceived as relevant. But let's see. So let's move on to our second goal, which is to identify a chemical and measure, most importantly, measure it across its concentrations range. And we're going to look at a very common chemical, which is ammonia. Now, ammonia is also a major industrial chemical, and it is used to produce fertilizers, pharmaceuticals, different refrigerants, and as an antimicrobial agent for the food industry. There are a lot of different industries involved with ammonia. It's a very widely used chemical. One additional example is that ammonia is actually used to produce munition, and it actually determines, or it results from its chemical properties. So ammonia is a colorless gas, but it has a very, very sharp, characteristic, very irritating and unpleasant odor, right? And I'm sure all of us have smelled ammonia at, one time in their lives. So ammonia is toxic. Flammability is not necessarily a big concern. It is flammable, but not highly flammable, not as highly flammable as benzene, for example, or methane, or other combustible hydrocarbons. But ammonia can violently react with some chemicals, such as those containing iodine, for example. Now imagine a situation where a train or a truck carrying anhydrous ammonia tips over. There is a release of ammonia. There is a leak in the refrigeration circuit, at a facility, let's say cold storage facility, for example. And ammonia is also used to produce illegal drugs. So whenever first responders, Homeland Security, police, and SWAT teams are involved with raiding Klan labs, ammonia is one of the concerns, in addition to phosphine, for example, among others. So what are the challenges in case there is an ammonia spill, ammonia leak, or a risk of excessive exposure to ammonia? Basically, excessive exposure to ammonia, right? Health of people involved related to the toxicity of ammonia is the biggest concern in that scenario. So what needs to happen from the gas detection standpoint? You need to be able to quickly identify ammonia, and you need to monitor for toxicity. But the challenge here is really, in many cases, first responders, for example, they face decisions when they cannot enter a premise without wearing personal protective equipment like their self-contained breathing apparatus and different levels of protective suits, right? So you need to not only measure ammonia at the permissible exposure levels, right? And we saw that these levels are at 50 ppm according to OSHA and 25 ppm, their recommended exposure limit according to NIOSH. Decisions on using personal protective equipment are made at for higher concentrations. And so we need to be able to measure fairly lower concentrations of ammonia, but still concentrations that may go beyond the range that can be measured by an electrochemical sensor, for example, right? So if you look at the sensing technologies that we have available to measure ammonia, right, from the toxicity standpoint, yes, there is an electrochemical sensor that's specific to ammonia, but in most cases there are some versions of an electrochemical sensor that can go and measure out to 1,000 ppm of ammonia, for example, but typical electrochemical sensors, they stop at around between 100 parts per million to 200 parts per million of ammonia. So for personal protection equipment decisions, you need to be higher than that. You need to be at around 200, 300 ppm, parts per million. Right? And the electrochemical sensor is not going to go that far out. So you have an option. You can use the tubes. For example, the range of tubes that we offer at Ray Systems here can go from lower parts per million out to up to 20-25% volume, right? So tubes are definitely an option to accomplish this goal from A to Z, but we know what the limitations of tubes as a detection technology are. So what we suggest is that you can see our respective customers and other listeners at this webinar that you consider an option to use an electrochemical sensors or tubes to identify ammonia in a specific fashion and also measure it at a lower range. Once you have to measure at a higher range, we suggest that you add a photoionization detector, which is a broadband tool, but it can still detect ammonia very well. And in combination, these two sets of tools, or two pairs of tools, PID with an electrochemical sensor and a PID with tubes, should provide a very good way of measuring ammonia. So schematically, it's going to look like this. You can smell ammonia, use it as a clue, right? If it's above 5 ppm, which is a fairly often met concentration of ammonia that you would have to deal with, then use a broadband sensor, such as the PID. If there is a response, use a specific tool like an electrochemical sensor or tubes. Or you can go the other way around. If you know that it is ammonia and you expect it to be in a lower concentration, you can use an electrochemical sensor or tubes first, but then if you can see that the concentration is going out of the range of these tools, add a PID to monitor at higher concentration levels. Now we have another polling question. Dave, back to you.
Yeah, the second question for you this afternoon. Are you currently practicing sensor fusion technology detection in your work as Michael has been describing in his presentation today? We've added a not sure option to the question here. And as you can see, as the answers come in, pretty even split between those that are using sensor fusion technology and those that are not. Slight percentage more are using than not. Not too many at all are in the category of not being sure. Not too many undecideds. But it looks, Michael, as though almost half of the audience today is certainly familiar with what you're talking about and, in fact, is using sensor fusion technology. And as we look at the final results, it doesn't take very long in this instant polling age for the results to come in. Are you currently practicing sensor fusion in your work? 49% say yes, 45% say no, and only 6% are not sure. Your thoughts on that, Michael?
I think it's really interesting. I mean, I was expecting that we will get quite a few customers who, quite a few listeners who actually practice sensor fusion, right? Because it just proves the point that it is a good way of really cost-effectively and easily accomplish gas detection goals like the ones we're covering here. So I'm really glad to see that almost 50% of our today's audience are actually using it. So I'm hoping that this webinar will provide them some additional ideas, and then the rest of the audience who are not using it yet may be able to find some benefits and actually look at it in more detail. So, Dave, if you're ready for me to proceed, then I'd like to look at our other example. And what we're going to talk about here is being able to use different technologies to cross-verify each other. So specifically, we're going to look at chlorine. So chlorine is a very, very widely known gas, right, and widely met gas. It is basically used as a chemical, but it's as an intermediate for production of other chemicals like polyvinyl chloride, which is used fairly widely as a plastic specific. A specific example would be the vinyl windows that are very popular these days. Chlorine is used as a disinfectant to purify water, and it's used in different household cleaners and bleaches. But at the same time, chlorine was used during World War I and during the Iraqi War in 2007 as a chemical weapon, because it has properties that are involved with irritating the respiratory system, right, and actually may cause death. There are a bunch of industries involved in the production use of chlorine, from basically consumer goods manufacturers that produce household cleaners, wastewater plants they use to treat sewage water there, bleaching in pulp and paper facilities, water purification broadly, like swimming pools, for example, and in the chemical industry. So chlorine is a greenish to yellow gas with a very strong odor. And, basically, if you're in a swimming pool, you can smell chlorine. This is how it smells. It's heavier than air. That's one of the reasons, in addition to its toxic qualities and irritating qualities, that's one of the reasons why it was used as a chemical weapon during the First World War, because it's heavier than air, and it kind of crawls over the ground, and soldiers who were in trenches were therefore exposed to chlorine. It was like a targeted way to reach those soldiers who were in trenches. It's extremely toxic, like I've already said. It irritates the respiratory system, it irritates the eyes, and when it gets into the lungs, it unfortunately reacts with water to form the hydrochloric acid, and basically that acid prevents people from being able to breathe when it forms in the lungs. So we have 1 parts per million TWA, that's an exposure over an 8-hour period according to the OSHA permissible exposure limit. And look at the IDLH, the concentration that's immediately dangerous to life and health. That's only 10 ppm. At that concentration, it's already dangerous for to life. So chlorine is not flammable. If we go to the next slide and look at a situation where there is a need to protect people involved or people who can be potentially exposed to chlorine in various industries that use chlorine. So the most important goal is to make sure that that people don't get overexposed. Okay? And really, if you use the electrochemical sensor for chlorine, like we discussed it, that sensor is prone to cross-sensitivity, right? It has a positive cross-sensitivity to the to nitrogen dioxide, which basically would cause the chlorine sensor to produce a much higher reading than in reality. But this is not as big a concern as a cross-sensitivity to hydrogen sulfide, which can actually cause the chlorine sensor to underreport its reading by as much as 30%. And remember, it is really important that chlorine be accurately measured at concentrations from basically 0 to 10 parts per million. Okay? So in a situation where, let's say, there is a person who is doing maintenance on a chlorine tank, right? An empty tank that needs to be painted, that needs to be it needs to be fixed, that needs to be repaired, that needs to be welded on. So imagine a situation where this tank was sitting empty for some time, and then there was basically a rat accidentally fell in that tank, and then a decomposing body of a rat can produce a lot of hydrogen sulfide, actually, up to a deadly concentration. So the chlorine tank would have some residual chlorine in it, and so there would be a need to measure chlorine, but also account for hydrogen sulfide. So what's the best way to do it? It is to basically use an electrochemical sensor in conjunction with a chlorine tube, right? Another option is to use an electrochemical sensor for chlorine and an electrochemical sensor for hydrogen sulfide. Okay, this approach where you use 2 different sensors allows the user to basically get a reading for chlorine and then get a reading for hydrogen sulfide. It is a more complex approach than just using the electrochemical sensor for chlorine and tubes, because when you use chlorine-specific tubes, you can actually get the true concentration of chlorine, right? If you use an electrochemical sensor for H2S to complement the chlorine sensor, the user would have to do the calculation, basically. Okay? So our recommendation for the easiest way to achieve reliable readings for chlorine is by combining the electrochemical sensor for chlorine with chlorine-specific colorimetric tubes. And of course, in this example, as well as in other examples where you're facing a chemical that has a very, very particular odor, use it as a clue. Now we're moving on to our last polling question. Dave, please, back to you.
Sure. Polling question number 3. How likely are you to practice sensor fusion? Very likely, maybe sometime in the future, not at all. Now keep in mind how the audience of professionals answered question number 2. So it's not surprising, I don't think, to see the responses that are coming in to this question. How likely are you to use to practice sensor fusion in the future? Given that there was about a 50-50 split between those who were using it already and those who weren't, now we're seeing that upwards of 60%, 58% to be precise, say they're very likely to practice sensor fusion in the future. about 40%, 39% say maybe sometime in the future, and a very scant minority, only 3%, see no reason at all and say no, not at all. They're not likely to practice sensor fusion technology. So it looks, Michael, as though we have about a 60-40 split here, with well over half of the audience saying that they're very likely to practice the technology that you've been talking about, sensor fusion, in the future.
I think these are fantastic numbers. I'm really delighted to see that basically either very likely or maybe sometime in the future is the response of 97% of our guests. And I personally think that this is great. I sincerely believe that sensor fusion can actually help enhance safety. And the fact that our guests are actually looking at it and considering it, regardless of what equipment they use, ray equipment, non-ray equipment, it doesn't matter. I think sensor fusion can actually help save lives. So moving on to our last topic that I wanted to cover. Before, in the previous slides, we looked at using sensor fusion to actually using different technologies to look at a particular one chemical. Now, I'd like to invite you to look at sensor fusion at a plant level, right? So basically, looking at all the chemicals that you have at your facility and being able to basically consolidate the readings from all the detection equipment that you employ at your facility, regardless of what gases that equipment detects, right? To consolidate all these readings on one screen. And that is something that is enabled by the modern wireless gas detection technology. And if we go to the next slide, this is what we're going to see if you deploy a system similar to what, for example, what Ray Systems offers, the ProRay Guardian wireless safety system, that consolidates data, real-time data, and alarm status, and location from different instruments deployed at a facility in real time, and provides you the visibility into their readings and alarm status, which results in better tactical awareness. You know what is going on. You can deploy redundant, you can deploy different sensors. You can see different instruments measuring the same chemical. Like, for example, we can see in the H2S column here, there are 3 instruments measuring for H2S. There are instruments measuring for other chemicals. There are also, there is a wind station that takes care of measuring wind, wind direction, wind speed, etc. And such a system allows you to really have all the tactical awareness of all the chemicals present at your facility, and getting the data from up to 512 different monitors at the same time. So it's basically, this is something that I think deserves to be called super sensor fusion, where you can use multiple sensors. You can use sensor fusion to detect and identify chemicals, and you can also use this wireless detection technology to aggregate data from all of your sensors so that you can know what is going on at your facility, and you can make decisions faster and potentially save lives. So in summary, what we looked at today is we saw how combining different detection technologies, how using sensor fusion can be more effective, more efficient than using individual portable detection technologies in isolation when you face the need to identify an unknown chemical, to measure it across the concentrations range, and to confirm the accuracy of the readings obtained by one detection technology with an independent other detection technology. We also briefly talked about how using modern wireless gas detection allows you to aggregate data from multiple detectors throughout your facility to perform sensor fusion at a plant level. So thank you very much for taking the time to join us today. This is the end of my slides, and let's see how many questions we can address in the remaining little time.
Yeah, we don't have much time, Michael, but I do have a couple of questions that if you could rather quickly go through, we'll cover as much ground as we can in a couple of minutes. First question, can you provide an update on current sensing technology?
An update on current sensing technology.
Yes.
So basically, I think the purpose of this webinar was really to do a quick overview of different sensing technologies that we have available. And I invite our guest who was asking this question to actually review the slides for more detail. I would like to also invite this guest to visit our website at www.racesystems.com, where we basically provide detailed information on the entire arsenal of portable and fixed gas and radiation detection technologies that we offer.
Okay. Mike, what is the best way to check for volatile organic compounds for air quality?
So basically, for air quality and volatile organic compounds, our biggest recommendation is to use photoionization detectors. It is a very good technology that is capable of pretty much covering a very broad range of different ionizable volatile organic compounds. We're talking over 300 of different compounds that can be seen by a photoionization detector. The air quality, the beauty of the PID is that it can go down to the parts per billion range, and for air quality decisions, that is something that is important. Being able to detect really low concentrations, trace concentrations of chemicals present. And a photoionization detector has the benefit of being a continuous monitor, so you can monitor trends and subtle changes of the concentration of these volatile organic compounds in ambient air.
Okay. One last question that we have time for, Mike. This user has a Mini-Ray 3000, and he is looking for ways to increase usage by speciation with other technologies. Do you have any recommendations?
Yeah, so I think some of the recommendations that we covered here, it's hard for me to provide a very specific answer because I don't know the application and what specific chemicals our guest is looking at detecting. But combining the photoionization detector with, which is the Mini-Ray 3000 is, combining that tool with specific tools, like for example, we looked at different tube options, right? The colorimetric tubes for benzene, butadiene, halocarbons are the tubes that can be combined to speciate, combined with the PID or fused with the PID, like we're using this term here, to actually provide not only accurate broadband detection for a fairly wide range of concentrations, but also speciate these chemicals. Also, combining a PID with electrochemical sensors, like we saw it for ammonia, is also a very, very good option.
Yeah, that's great, Mike. That's the time has run out on the webinar clock. Is there an email address that people could use? Because there are questions that we didn't get around for you to be able to answer. If post-webinar, some attendees wanted to email you their specific questions.
Oh, absolutely, David. We would love to take the questions. We know that we didn't have a lot of time to cover the questions during the webinar. And there is an email where we'll be happy to receive the questions. The address is events@racesystems.com. EVENTS, events@raesystems.com.
That sounds easy enough, Michael. This concludes today's webinar, folks. So again, please join me in thanking Michael Weinstein for his excellent presentation, covering an awful lot of ground in 60 minutes, as well as our sponsor, Ray Systems. As you exit today's webinar, again, please take a couple of minutes to complete our survey. We strongly welcome your detailed comments to help us serve you better. If you have any additional questions or comments, don't hesitate to contact me, Dave Johnson, at johnsond@bnpmedia.com. Please visit webinars.ishn.com for the archive of Michael's presentation today, as well as information about ISHN's upcoming events. We certainly appreciate your time today and hope that you have found this webinar to be a valuable experience. Good afternoon, everyone.